Hello everyone. First of all, thank you very much to the organizers for putting up this LIGO symposium under such special conditions and for giving me the opportunity of presenting this work that I have done with Andrea Caputo, Sberna, Babak, Enrico Barausse, Sylvain Marsat and Paolo Pani on multi-messenger and multiband observations of accreting black hole binaries. As you all know, LIGO will be sensitive to gravitational waves at lower frequencies as compared to current detectors LIGO and Virgo. Therefore, it will observe different sources and also will be sensitive to properties that are relevant at low frequencies. Moreover, some of the systems that will be observed by ground-based detectors could be observed by LIGO for years before leaving the LIGO band and merging within a few weeks in ground-based detectors band, offering the possibility of a multi-band observation. And observing a binary over such an extended frequency range allows to probe for very small effects affecting the gravitational wave signal. These effects could be due to modified gravity or to the environment around the binary, such as the presence of gas and that would be accreted into the black holes. So to give a bit more context to this possibility, in this work we will consider two kinds of sources. The first one are stellar mass black hole binaries, which are the ones that have been observed by LIGO and Virgo so far, which contain black holes with masses up to 50 or 60 solar masses each. And it is thought that some of the ultraluminous X-ray binaries that we observe could contain such black holes that would be accreting at extremely high rate, eventually much above the Eddington rate. Another possibility for ultraluminous X-ray binaries is that they contain less accreting but more massive black holes, the so-called intermediate massive black holes. Several scenarios have been proposed for the formation of these IMBHs, but they have not clearly been identified yet. However, we could consider binaries formed of such black holes where individual masses would range from 10 to the 2 to 10 to the 5 solar masses. And an additional, so a possibility for having accreting black holes in a binary would be, for example, near an AGN, as has been recently suggested, where a lot of gas would be present that could feed the black holes during their evolution. So, to give a bit more details, we measure the rate at which the black holes accrete with respect to the Eddington rate, which is the rate at which a black hole accretes when the disk around it is at equilibrium. And so we introduce this Eddington ratio, which is the ratio between the rate and the Eddington rate, that we assume this Eddington ratio to be constant throughout the evolution and to be the same for each black hole. Then we compute the effect on the waveform, and we find that this affects the phase at a -4 post-Newtonian order, which is lower frequencies as compared to the leading order in general relativity. So this means that, and then since this is a low frequency effect, LIGO could eventually be much more sensitive to it, will be much more sensitive to it than ground-based detectors. So to estimate the detectability of this effect, first we generate a mock astrophysical catalog, and we use a Fisher analysis to estimate the error that we would make on the Eddington ratio for each of the detectable events in this astrophysical catalog. So we consider a value of 1 for Eddington ratio, which means Eddington accretion, and 10, so which would be a super-Eddington accretion. Moreover, we consider 2 scenarios where we use LISA observations only, and the other one that we use to mimic a multiband observation that we name LISA plus Earth, in which case we consider the time to coalescence to be measured by ground-based detectors, and this allows this adds additional constraints and allows for better measurement of the Eddington ratio. It is important, however, to keep in mind that real multiband detection would also bring more information than the time to coalescence, and therefore our analysis can be seen as a conservative multiband analysis. Now, what we find is that in each scenario, LISA only and LISA plus Earth, basically we could detect accretion only if it happens at Eddington or better super-Eddington level. To confirm this, we perform a more refined analysis where we focus on one GW150914-like system, and we generate data that contains the effect of accretion and perform a full Bayesian analysis to recover the posterior distribution. Now what we find is that in the case where we have Eddington level accretion, the posterior distribution of the Eddington ratio is compatible with 0 even in the LISA plus Earth scenario, which means that we could not safely claim for the presence of this effect. Now, in the case we have super-Eddington accretion, for example, Eddington ratio 10, we find that already in the LISA only scenario, the distribution is not compatible with 0, which means that we could claim detection, and with an even higher precision in the LISA plus Earth scenario. Next, we consider intermediate mass black hole binaries. So here we will focus on one system accreting at Eddington level, and we consider different distances. And what we find is that if the binary is close enough, so for example at redshift 0.1, we could detect Eddington level accretion. Now if the binary is too far, redshift 0.5, we could not safely claim for the detection of this effect in the gravitational wave signal. Next, so inspired by the recent suggestion, we investigate a system that is compatible with what is claimed to be the electromagnetic counterpart of the black hole binary merger near an AGN. So we take a system at 3 gigaparsecs of masses 85 and 65 solar masses, and for the angles, so sky location, inclination of the binary, polarization, initial phase, we draw 5,000 random realizations of these angles. We compute the SNR using a threshold of 8, and we find that in 17% of the cases we could detect such a system. In other cases where the system would be detectable, we perform a Fisher analysis to estimate the error on the Eddington ratio. And what we find is that even in the LISA plus Earth scenario, we would need Eddington accretion, an Eddington ratio above 4 in order to be able to detect it. But once again, keep in mind that this LISA plus Earth scenario is conservative, and that with a real multiband detection, we would have much more constraints on the other intrinsic parameters of the system, not only the time to coalescence, and this could improve a lot this result. Next, we turn now to the electromagnetic counterparts. And because LISA will observe these binaries for such a long time, very long time, the precision on the sky location is extremely good. So below 0.4 square degrees, which is much better than the binary neutron star, for example, as you can see in this picture. And this is within the field of view of next generation electromagnetic instruments, such as the X-ray telescope Athena or the radio telescope SKA. And so we can compute the emission in both bands, X-ray and radio. So by these black hole binaries, and estimate if they would be observable by these telescopes with an integration time below 1 day. What we find is that for intermediate mass black holes, we could detect the flare emitted at the moment of the merger in the radio band and the X-ray emitted during the spiral with Athena. But for stellar mass, we would need a longer integration time, making it unrealistic that we can detect the counterpart. However, it was once again in this recent paper on the counterpart to the black hole binary merger, it was suggested that the counterpart could come from the propagation of the black hole remnant in the gas around the AGN. So this is an additional possibility of counterpart that we have not investigated. So to summarize, our Fisher and MCMC analysis have confirmed that if we have accretion at Eddington or super-Eddington level, we could eventually detect them in both stellar and intermediate mass black holes. And for the later, so for IMBHs, we could detect an EM counterpart both in the radio and X-ray band. So this is a great opportunity because it would allow first for a more precise measurement of the Hubble constant, for example. Also to understand the mechanisms of black hole formation and accretion. And finally, it's very important to always account for the possibility of having these or other environmental effects, so that we do not we are not fooled and do not consider them to be due to modification. So in order to disentangle them from modifications of gravity. Thank you very much for your attention.